technology has given us tools that we can use to do remote sensing with technology that gives us better capability. So we can use cameras, telescopes, and more importantly, radar. So here's a picture of Utah from space with an optical system. And if we think about remote sensing, it's seeing things from a distance. We start from far, far away. And as we move in closer, we end up kind of at the view where we as humans see things, okay? All of this is based on our ability to sense electromagnetic waves. Now, as electrical engineering, that's what we deal with. We deal with radio waves all the way up to the gamma rays. And of course, we use optical remote sensing, visible light, to do a lot of our capability. Well, these, just like the visible light has colors, radio waves, microwaves have colors that can sense different things. So when I was young, I had a lot of freckles growing up. Now I don't have so much hair to cover them up. My mother said the Lord must have loved me because he gave me lots of sun kisses. As I've gotten older, they've kind of faded away. But if I go into an RGB image, you could still see those freckles on there. It just shows that you could see different things at different frequencies. The same thing's true when we look at radar. The different wavelengths of the electromagnetic signals can see different features on the Earth, which gives us a chance to examine the Earth in new ways. As engineers, our job is to develop the technology to allow us to do that. So one of the advantages of microwave radar, which is what I work with, is the fact the radar can penetrate right through clouds. And so we can study the surface characteristics, which basically are the surface roughness and the dielectric properties, what the surface is made out of. But we can understand the environment. We can provide the scientists the input that they need to draw, more scientific things about weather and climate and other things. So one of the projects that I've worked on the most is wind scatterometry. In wind scatterometry, we put a radar on a spacecraft. So here on the left is a picture of the QuickSat satellite. This was launched in 1999. It includes a rotating antenna. Up in the upper right, you can kind of see how that rotating antenna works. It sends out pulses of energy that bounce off the ocean surface. Now, if we kind of look at the ocean surface, it's all full of waves, that center picture. But on those big waves are smaller waves. Those waves that are, a few centimeters to 5 or 10 centimeters long are called cat's paws. These capillary gravity waves are in equilibrium with the wind, which means as the wind blows, those waves are created. The more the wind blows, the higher speed it is, the stronger the return echo, the bigger the roughness. Most significantly, as the wind blows, it creates these large-scale patterns. And if we look across those troughs versus along the troughs, we can actually determine the wind direction. So the secret to measuring wind from space is actually to look at the waves on the surface of the ocean. So I've got some examples here of a hurricane and also some images that we made here at BYU looking at the Earth as a whole. Now, the data that's collected by the scatterometer not only covers the ocean, but also the land. And that's where this story gets interesting. So here is an animation of a set of optical images taken from a geosynchronous satellite looking at Hurricane Isabel, which hit the coast of South Carolina back in, it's been quite a few years now. But as it did so, you see it starts out dark, and as the movie progresses, it gets light. And we're seeing 1 day's worth of data. The difficulty is we're only seeing the cloud tops. We don't know what's going on at the surface, which is what we really care about with things. But we have that radar up in there. And if we look at the radar signal, we can actually get some information about the surface, can penetrate the clouds. So these little arrows that you see here represent the path of this satellite radar over this same area. And the colors give us something about the wind speed. They tell us the wind speed. The arrow direction gives us the wind direction. And if I zoom in on that red box, we developed some signal processing algorithms that allows us to take that scatterometer data at that lower resolution and make it very fine resolution. Now, the original picture I showed here, the wind vectors are 25 kilometers apart. Okay, so that's enough that the weather forecasters are just totally amazed because we've given them more data than they've ever had. The problem with forecasting the weather in the future is you have to know what it is now The radar data gives us that. But they wanted finer resolution data. And so we did some signal processing techniques to make even finer resolution. So now we get down to 2 or 3 kilometer resolution, which allows us to resolve things like the eye, the hurricane eye in the center. So we captured it just as it was going on to the Outer Banks there in South Carolina. Now, the sensor measures wind. So here's an example of winds blowing over Hawaii. So those black wind barbs gives us the wind direction, and they tell us something about the wind speed. The islands of Hawaii stick up really high, and so the wind has to go around it. If you notice, as the wind goes from the right to the left, it accelerates, that is, it goes at higher wind speeds around the outside. Well, when we first showed this data to people, they were really impressed because they had never really seen this data this way. But they were a little curious about the noise, the little dots out there that were in the tail of this. And those are actually thunderstorms that were created by the turbulent atmosphere generated as the wind goes around Antarctica. So some of my students and I began to process data. We made these higher resolution pictures. We developed ways to eliminate the effects of land contamination. And we led us to do all kinds of interesting things. The data could be used not only over the ocean, but over land. This is a radar backscatter measurement, that is the amount of reflected power, echo strength, over South America. So the lighter area here represent jungles, vines, Tarzan of the apes, all that kind of stuff. The lighter areas are could be woodlands and grasslands up in there, so it's not so jungly. And we took a radar image collected in 1978 and 1996, and we looked at the difference between the two. And where there were significant differences, we put in colors. The pink represents the most significant color. The yellow represents a less change. And if we ignore the mountain snow changes there on the left, other areas represent changes in vegetation. So, if we kind of look at that picture, you can see, well, along the Amazon River, we see some changes on the banks. There's that little pink dot up in there. That's the result of when the Brazilian government dammed off the Manaus River, and that's the lake that was produced behind that. We can see that. And if you look, you kind of see some lines in some of the colors there. Those represent where the government has built roads. People go along the roads, stop along the side, cut down the trees, grow crops for a while. The land is exhausted, and we get deforestation. Okay, so this gives us an idea about how much deforestation. This deforestation is particularly prevalent on the right-hand side, where there are coastal rainforests and other forest woodland areas that are being cut down at a significant rate. All right, so what does all this have to do with icebergs? Well, this is where the story gets kind of fun. Back in the early part of the 20th century, there was a famous ship that struck an iceberg and sank and resulted in a bunch of movies, okay, and stories. Well, the reason that ship ran into the iceberg is no one knew it was there. As a result of this tragedy, the governments of the world got together and formed the National Ice Patrol, the International Ice Patrol, which tries to monitor icebergs so that ships can avoid them. Sometimes they lose a few. Here is a picture that shows radar backscatter of the Earth at the South Pole. This was made with the first sample of data that we got from that QuickSat satellite that I showed you earlier. The bright area in the middle is the continent of Antarctica. The grayer area on the outside is sea ice. And the ocean was masked off to make this picture a pretty picture. And in so doing, we discovered some blobs, those white blobs out there. Those are icebergs or major islands up in there. Now, the upper right, the top island up there is South Georgia Island, which is famous from Shackleton, where he ended up there. But B10A was a large iceberg that we discovered in these images. And when I called the National Ice Center, which is part of the International Ice Patrol, to get the name of this iceberg, they were really surprised because they had lost track of this iceberg 4 months earlier, and it had drifting into a shipping lane in the Drake Passage. So they were grateful to know that. And this started BYU along the iceberg track. So we went back and started tracking icebergs in these radar images we collected, going back from the beginning of the space age up to the present. Now, off to the left is a picture of that iceberg, B10A. This is an optical photograph that's kind of been false color enhanced so that you can see it. And the scale of this is surprising. The height of that iceberg is 65 nautical miles wide by 25 nautical miles wide. That's bigger from Nephi to north of Salt Lake in Utah. And the little dandruff you see down in the lower right, those are 1 kilometer sized iceberg bits that have cracked off that iceberg. And you can kind of see the problem with tracking an iceberg is because it's basically the same color as clouds. And also in near the poles during the winter, it's dark, so you can't see icebergs. In the animated sequence that you can see on the right, we can track these icebergs. And there's like a couple of mating paramecium dancing out there. B10A was one that we discovered that was been lost. A22 was one that was known. These icebergs broke off an ice shelf in Antarctica, drifted out into the open ocean. And as you examine this movie, you can see the movement of sea ice and this kind of gray stuff that's around the outside. That's actually the surface signature, the roughness, that the instrument was designed to measure. And yet we can do some pretty amazing things with looking at ice and other things with this data. So if we were to go up and look at this iceberg, here is a view. We helped navigate some ships to study these icebergs, and 9/10 of an iceberg is below the surface. So as they got closest, they realized the iceberg was 60 feet tall above the surface of the water, which meant that it dropped 600 feet deep. This is a pretty good sized iceberg. This is another picture of a different iceberg, a somewhat smaller one. This is only 25 by 12 miles. These Antarctic icebergs are really big compared to the ones there in Greenland. This is a picture taken by an astronaut from the space station. And for many years, we supplied information to the astronauts to help them know where to look to find these icebergs to photograph. It's kind of one of their favorite hobbies up in there. Again, the clouds make it difficult to see the iceberg. Fortunately, in this case, it only partially covered it. We have been working with scientists who want to study icebergs as a proxy for the breakup of ice shelves in Antarctica. As these melt and fall apart, that helps them understand the process of how such a big chunk of ice can melt. As a result of this work, we ended up generating a database that now spans nearly 40 years worth of data using radar information to track all the icebergs. And here's an example of that. We developed the signal processing algorithms and all the image processing, and we provide this data to the National Ice Center, which means that BYU students, most of whom have never seen an iceberg, I've never seen icebergs, but by remote sensing, we can still do this from half the world away. So the question came up when we started looking at this data. The National Ice Center's iceberg track was this blue line, which in this plot extends from the 1970s up into the present. And people noticed when we started doing the study in the late 1990s, there's almost an exponential increase in the number of icebergs. And they wondered, is this some sort of evidence of global warming? And we said, let's find out. And so we went back to our data, and our first radar observations occurred back in the 1970s, and we found out that the National Ice Center's iceberg count was way low. They hadn't counted enough. And then later, their count went up. Well, we examined their data set, and we found out that each time there was a jump in those early days, it's because they changed sensors. They went from kind of relying on ship reports to using the first satellites in the late 1980s. Then they started using these optical satellites. Our data begins in kind of the mid-1990s when we're starting to use the radar data. And then in 1999, which is when I made that first picture, there was a major calving event. Calving event is when the iceberg breaks off of an ice shelf. This is an event that occurs about every 50 or 60 years on each of the major shelves. Another one occurred in about 2001. And the large jumps are associated with the break-off, the calving of these icebergs, and then their eventual disintegration. Nevertheless, our data sets, these pink lines and some of the other lighter color lines, show that they're still undercounting the number of icebergs. So our conclusion from a scientific perspective, that while there's evidence of localized warming in Antarctica, the ice sheets are thinning, the iceberg data count in the early 1900s and 2000s could not be used to support global warming because most of the increase that we observed in the data sets was due to improved tracking technology or was associated with the calving of these ice sheets, which occurs every 50 or 60 years. And the last time it happened was 50 or 60 years ago. So that was kind of an interesting result and kind of a strange thing for a bunch of electrical engineers building radar systems to do. But it goes to show you the serendipitous application of remote sensing in our study of the world. I want to turn to the largest island in the world for Greenland for just a moment. There, the snow has been accumulated there for tens of thousands of years, and the ice up there is more than a mile thick. This ice, because it piles so high, the weight of the ice actually causes it to flow, becomes a glacier. So the peak mountain is very tall, but the ice flows off to the sides. And as it does, it gets a little lower, and therefore it can melt. So along the edges of the ice sheet, the ice melts a little bit and water flows off into the ocean. Greenland's very sensitive to climate conditions. That is, warming conditions cause more melting. And the radar backscatter that we're using to observe this is exquisitely sensitive to the presence of liquid water. So if we start with frozen water, it has a dielectric constant of about 4. Liquid water has a dielectric constant of about 81. That dramatic change in the dielectric constant of the material shows up as a difference in the backscatter value, which allows us to really determine where the melt occurs and to some degree how much melt occurs and where it comes. It gives us a melt extent and history for that. So here's kind of a cool, pun intended, picture of Antarctica. This one is a false color image where we've combined multiple radar images together, different frequencies, different polarizations, to make a map of Greenland during the summer season. Around the outside, the color is purple because it's dominated by low frequency backscatter. That's the blue ASCAT, with some of the others to a lesser degree. In this image, the ocean is kind of black because there's not a lot of backscatter. We picked a very good day. At the very far north up there, you can see kind of a lighter purple. That's where the polar ice cap is. We'll talk about that in a minute. As you move inland toward the island, there's a darker band, then there's a white band, then there's a golden center. The golden center corresponds to the unmelted ice. The white area is where the melt has occurred in previous times. The water percolates down into the ocean and into the ice, and then snow, and then refreezes. That leaves ice bodies, sometimes called ice glands or ice lens, that act as volume scatterers that when the radar signal comes into the snow, increases the amount of backscatter, which causes it to look bright. And because these glands are quite large, they reflect all the frequencies pretty equally, it ends up being white. Downslope of that, close to the purple area, that darker band around the outside is where the snow is wet due to melting conditions. So we can track that up in there. And the varying gold color tells us something about the amount of accumulation that has occurred up there. If I take just a single frequency and make it into a slightly different color scheme just for convenience here, and I go from winter to summer, during winter, the outer edge is now kind of bright, lighter colored. And then the summer occurs, it gets dark because the reflection is not coming back toward the radar, but bouncing away from it. So it looks dark where it's melting, and then it refreezes. So we can track the melting location and the amount of melt. So I've got a couple of points down on the bottom that shows the backscatter value, which drops when it melts, comes back up when it refreezes, melts. And over the summer, this happens several times along the coast. And then another area, it stayed much meltier for a longer period of time. Well, this area of extent of melt is perhaps different for every year, but we have a long data set. This gives us a chance to look at climate over decades instead of just 1 year, which is weather. So here is a set of images of Greenland that we've made using radar data collected from satellites that we processed here at BYU. We took data that was collected in 1978 through the present day, and this series now extends with similar trends. But I'm just showing a few pictures here. I took the average backscatter image, and this is the difference from the average. So on the left, the darker area is where there were changes that were associated with melting changes. So as we go from 1970 to 2008, that darker turning to light area corresponds to where more melt has occurred, and then it's refrozen to make it brighter in the future. In the upper part of Greenland, there's been more accumulation. In other words, it was brighter in the older images than in the present because the accumulation buries underlying layers, which suppresses some of the surface scattering that occurs in the interannual layers in the snow. So this time series shows that there's more melting going on in Greenland, but also more accumulation. Both of those are consistent with a general trend in warming conditions in Greenland. The melting, obvious reason, it's warming during the summer, so it melts more. The accumulation is because a warmer atmosphere carries more water, which results in more precipitation, which comes as more snow accumulation in the upper reaches of Greenland. This is direct evidence of changes in a multi-decadal period in Greenland, warming conditions in Greenland. So if we think about this, really this suggests that there's a climate change. Climate is something that happens, it's average weather, but it happens over a long time. And there are a lot of possibilities of why this occurs. There's a lot of reasons for this to be. So let's kind of look at the climate for a little bit and how radar observations can fit in that. In the poles, wind blows and it freezes. During the winter, the ocean starts to freeze. Well, the salt waters like to freeze, so as the ice freezes, it squeezes the salt out, and now some of the salty water sinks to the bottom. It's now colder, denser than the water, sinks to the bottom, flows along the bottom of the ocean, where it's warmed up, shown as red here. That warmer water flows back to the Arctic, where this cycle continues. This is called the thermal haline solution, salt heat. That circulation that drives the climate, which keeps the poles from being too cold and the equator from being too warm for us. This is driven by polar conditions happening both the northern hemisphere coming off the coast of Greenland and in the southern hemisphere coming off the coast of Antarctica. Well, our backscatter data is particularly sensitive to this data, to the melting condition, so we can track this. Let's take a look at that. In particular, let's look at Antarctic sea ice. On the right-hand side here, I've got an animation, multicolored, doing the frequency to the multi-channel radar that we showed before, that shows the change over multiple years of Antarctica. Each year, during the summer, it melts back, and then as the winter comes along, the ice sheet grows back out. That's the sea ice. You're seeing the growing there. That stuff going on around the outside are storms going around and wind and waves on the surface of the ocean. If you look, there we go with melting again. If you look really carefully, you can see some bright white dots moving. Those are icebergs moving up in this. Now, from year to year, this is about the same cycle every year. Fortunately, Antarctica, until very recently, hasn't really changed very much, but it has been changing some. During the melt season, the freshwater ice melts and it leaves a freshwater layer that then has to mix with the ocean, and that helps bring nutrients in to feed penguins and those other kind of animals. During the winter, as that ice forms, we get a lot of this circulation, Antarctic water bottom formation, which is where they get salt-enhanced, briny water that sinks to the bottom and flows along. Okay, so this is an important thing that these radar observations go and help scientists understand the thermal transfer between the ocean and the ice that affects the overall climate of the Earth. Switching to the northern hemisphere, the lighter gold in the center here is the permanent polar ice cap. We call that multi-year ice, and as warm fronts move over that, they melt the surface. So we see that as swirly dark colors that melts back to just that permanent ice pack. And then the ice, in the winter, the ice grows with first year, which is a thinner ice layer. First year ice is maybe 1 to 2, 3 meters thick, but multi-year ice could be as thick as 17 meters or so. That's the average thickness of that. And that insulates the cold atmosphere from the ocean. Where that insulation disappears, you have water, that bottom water formation we talked about earlier. if we look at this climate time series very carefully, we can see over years that brighter gold, the permanent ice pack, has been shrinking. Now, the primary reason it's been shrinking is because it's evecting, that is moving down the east coast of Greenland, moving into the North Atlantic where it melts. That movement of that ice, which is driven by weather conditions and also melting conditions up there, affects the formation and the circulation of this bottom water that we've been talking about. Remember, the circulation brings warm water from, say, the Gulf of Mexico along the east coast of the United States, across the North Atlantic, and helps keep England and Northern Europe in warmer conditions than would otherwise be. Otherwise, it would be a lot like Siberia, which is just at the same latitude, but further to the west. This freshwater influx of this freshwater ice coming down there affects that thermal haline solution circulation in a way that affects the general general weather conditions in the ocean. The temperature distribution affects things even as far away as the hurricane belt, which is down near the equator, coming off of Antarctica and moving toward North America. Here is a sequence of images where the light white shows our radar observations of this permanent ice pack. And from 2003 to 2009, and continuing to the present, the amount of permanent ice pack has been shrinking. Now, here's the interesting part. The first year ice, which is formed in the winter, extends about the same amount, but in the summer, it's been shrinking back, getting smaller and smaller. So we've got a time series. I'm missing it. I have a time series of this that shows this process. I want to change topics for a minute, though, and talk about the BYU synthetic aperture radar experience. We've been doing, as many of you know, a lot of rather interesting work in looking at synthetic aperture radars. When I started here in the 1990s, we began developing smaller radars. The radar I worked with at JPL occupied half of a DC-8, and so we decided we could shrink them until they'd fit into basically a Piper Cub or a small Cessna plane. And these pictures show some development of some of our radars, and we shrunk them down smaller and smaller, and showing some of the pictures that we've worked with. One of the more interesting projects we worked on was the BYU Interferometric SAR, where we used commercial off-the-shelf equipment to build a rather sophisticated interferometric SAR, which was capable of measuring topography as well as creating radar images at very high resolution. So here's an example of some high resolution radars collected with that interferometric system. In the lower right down there, you can see the extracted topography along with the SAR image that's been draped over it. And this was just collected by flying the aircraft along and taking the radar images and showing a little panel of the image and making it animated up in there. In urban areas, we can see lots of bright things, but we can also get a lot of information about vegetation, land use, and many other applications. Most recently in the MERS lab, we've been looking at flying spacecraft. So back before the pandemic, our team put together, designed and built, an all-student team, built a set of spacecraft, which we call Passive Inspection CubeSats, or PICs. These are example of those. This is basically a flash camera. So we're showing in the upper movie there, you can see kind of the deployment of the antennas. These things, these 10-centimeter cubes are in a Pez dispenser. Basically, they're in a square tube with a spring on it. They flip open the door. These things are popped out by the spring. The antennas pop out. And in this case, we arranged ours to have cameras. So those little circles in the middle are video cameras, so we could take pictures of our own deployment. And we had to include a flash camera because we would be deployed in the dark, and so we could take pictures of that. This was entirely assembled, designed, and built and tested by students. It was launched in January 2021. We launched 2 of them. They were launched from an air-dropped rocket. So this is the Virgin Orbit 747 dropping a rocket from the wing. You can see the rocket just starting its engine to fire up there, went up into space, delivered our spacecraft. And this picture up here shows our two spacecraft, and you can see the flash coming off our spacecraft, and it's actually illuminating the deployment vehicle from which it came from, the second stage of this rocket. And so this has been an exciting effort. We're continuing this effort with some new ones, building more of these small CubeSats. We're doing capstone projects and other research projects to sort of expand, so to speak, BYU's influence to not just the Earth, but up into space. And so that's my talk. Are there any questions from the peanut gallery out in the webinar? I'd like to thank everybody for participating in this. I hope you found it interesting. The research has been very fun for my students. We found it cool, pun intended. We've really liked being able to see so many different things and do so many things. Really, this has been a great tool to help students understand remote sensing stuff. I've got a question here that says from Tom Carlincy, a student who used to be in the MERS lab many years ago. Besides illuminating the deployment vehicle, is there a purpose to the flash on the PIX spacecraft? And the answer is no. Their primary purpose was just to illuminate as they moved away from the spacecraft, because we were worried to be in the dark. We actually only flashed it during that initial going out, so it flashes several times. We see it as one flash, but it's actually a series of pictures that are being taken in there. Thank you for your question, Tom. I got a question here from Tyson Louder. Has BYU Center for Remote Sensing looked at data from LiDAR-based satellites, such as ICEsat, or do you primarily look at data from radar-based or passive sensors? Short answer is we emphasize radar-based and have done quite a bit of work with passive microwave sensors. We are doing some work with some LiDAR most recently, looking at cloud distribution, the particle size distribution in clouds. Our interest primarily has been in modeling the backscatter characteristics of the cloud. We're using the LiDAR data for that. There are other scientists who are using it to look at the topography of the ice and some of the things. Our radar data supplements that. The LiDAR is a little bit more precise than our data because they can get the topography directly a little bit easier than we can, but they have a very narrow swath. Whereas we cover the globe many times a day, they just get a line on this. So it's kind of a nice complementary sensor. We could put their data into a global context. Thank you for your question. Bill Allen, do you have any AI machine learning technology to predict movement? Yes, we've got work doing on that now. I'm not prepared to talk about it here because we're still working on, students are still doing it, and we're hoping to do some more. We've done some previous non-AI based stuff where we're looking at automated ice motion. That's been kind of fun. And yeah, we hope to keep doing even more of that. From Jared McBride, the question is, what is the next area of focus for your research? Well, we're looking at advanced antennas to go on spacecraft. One of the big problems with some of the microwave sensors we have is they use gigantic antennas, which are hard to fit on small spacecraft. So we're working with we have some NASA money to research a metamaterial lens. So it's actually a series of membranes. Think of saran wrap or a Kapton foil, put some copper on it, arrange in the right way, you make resonant features in there, and you can make a material whose dielectric constant is anything you want, even negative numbers, which is really interesting, although that's not what we're doing. But that allows us to make a signal that we can make the lens flat. It's very lightweight. We can rotate it. We illuminate it from the top. It directs the beam off to the side through the lens, and we can eliminate a gigantic, heavy, awkward reflector. So this program is known as GLOWS, which stands for the Global L-Band Ocean Water Cycle Observatory. So we're hoping to launch that sometime in the future as a follow-on to the SMAP, Soil Moisture Active Passive mission, which is up there now. I'm actually the PI for that. had students working on that. It's kind of a fun process. So we're focusing our lens using metamaterial. That's kind of fun. Question from Joel Jackson. Looks like you've come a long way since CSAT in the Amazon days in 1991. Yes, we've come a long way. We're still doing a lot about that. Next question from Tom Carlinci again. As a student, I remember you saying that the climate is like a control system, and like any control system, when it starts to become unstable, we see large changes. Is that still your opinion? Yes, it is. We have been in a terrible drought here in the West for the last few years. At my house last year, not this year, but the year before, we got a significant snowfall in November. We didn't get precipitation of any measurable amount until October the following year. This year, we've got more than our store. So we're going flopping forth between too wet and too dry. So this is, makes me wonder a little bit. Things are, there's some evidence that being unstable associated, we're getting to a tipping point on some things. Just my opinion. From Brian Fisk. Have you ever performed animal surveys such as flocks of birds? I've not, but ground-based radar systems regularly track flocks of birds. We've done some research studies where we provided radar imagery that was used to track, to measure vegetation. Have done some capstone projects where we've radar sensors to observe and detect polar bears, mainly to do polar bears in their dens. I can't talk too much about that at this point, but that's an active project we've been doing, a paper that's coming on about that, some of our work on that shortly. Thank you for your great questions. Last set of questions, and I think we run out of time. Okay, thank you all for participating in this webinar. I hope feel like it was worth your time. There's lots of fun research going on here at BYU, not just in my area, but we've got a lot of new faculty. We're really excited. The electrical engineering program is just booming with lots of work. And so I'm just totally grateful to have been here so long and do so many funny things, and looking forward to continue to doing it for yet longer. Go forth and do good things as engineers. Make us proud. Thank you.
And David, before you turn it off, I just want to announce that next month we will have Dr. DJ Lee. I don't know his topic yet, but I'm sure it'll involve vision systems, smart self-driving cars, something along those lines. That will again be the third Friday of the month at noon Mountain Standard Time. And I think we've now figured it out where we will be live streaming on our YouTube channel at the same time. I got it up and running here for us, so it's been running live here. So look for us next month. And Dr. Long, thank you so much. We appreciate it.